All right, let's do a short video looking at parametric and really focusing on dy dx and the second derivative of y with respect to x, and compare that to dy dt and dx dt. So dx dt and dy dt, right? This is the time derivative of horizontal position, which then is horizontal velocity. Well, this is then vertical velocity, and those are just subscripts, right? I mean, these I think make a lot of sense. If we take another derivative of dx dt, meaning we're taking a time derivative of the horizontal velocity, which we usually say x double prime, that then is just horizontal acceleration. Y double prime, which does not mean the second derivative of y with respect to x. This is the second derivative of y with respect to time. Well, that of course is vertical acceleration. Those make sense. If I asked you to find the speed of an object, well, that is by definition the magnitude, meaning the size of the velocity vector. Well, the velocity vector is moving so fast horizontally and so fast vertically. The magnitude of the vector is the length of the hypotenuse. So it makes sense then that the speed at any moment in time is the Pythagorean theorem of the horizontal speed. Again, it's speed because we end up squaring it. Right, it's always a positive once you square it. And then dy dt. Okay, the magnitude of this vector, this length is dx dt. And I made them both positive. I made it going to the right and going up, but it wouldn't matter, right? You're squaring them, so it was going left and down or whatever. The magnitude of this vector is the speed. So the speed clearly is related to both velocity vectors. The velocity vectors are dx dt and dy dt, and acceleration vectors are those. Okay, so we really get to the harder parts. Dy dx. Well, it turns out we don't have y as a function of x. If we did, we would just take the derivative, right? We are given, well, lots of times we're just given dx dt and dy dt, but we're given x as a function of time and y is a function of time. You can't take the derivative of y with respect to x because there is no x in here, they're times. So really what you're gonna do, you're gonna use the chain rule. You're gonna take the derivative of y with respect to time because y is a function of time, and then you're going to multiply by, oops, darn it. You're going to multiply by dt dx, okay? And you can see that the dt here and the dt here would cancel and you'd be left with this. Now, this is not what I told you to do in class, right? Because it doesn't really make any physical sense. Why would you multiply by dt dx when you have x as a function of time, not time as a function of x? But if you put this in the denominator, we then have dy dt, and instead of multiplying by dt dx, we can just divide by dx dt. This makes sense. I proved it to you using the chain rule of why this actually works, but this also makes sense because dy dx is the slope on an xy graph. And it does make sense to us that the direction, meaning the slope, is related to how fast you're going vertical and how fast you're going horizontal. Meaning, if somehow this was, you were going 2 meters per second vertically and 1 meter per second horizontally, then at that moment, you'd be heading in this direction. You'd be going 2 meters up for every 1 meter to the right during that second. That does make sense that that's the slope. So I think the slope formula, dy dt over dx dt, makes total sense. However, it comes from the chain rule right here. The one that you guys don't like, and I don't like it either, is this one. The second derivative of y with respect to x. Again, it's not acceleration. Just like dy dx is not speed. This is speed. This is velocity. Velocity is a vector. Dy dx is slope on an xy graph. d2y over dx squared is curvature. It's not acceleration, okay? The second derivative here is acceleration. So if you were looking at an x versus t graph, the second derivative is horizontal acceleration. The curvature is acceleration. But we're not looking at an x versus t or y versus t. We're looking at an x versus y graph. An x versus y graph, it's still concavity. This is concavity. And how do you find it? Well, let's just pretend I had z, and it was some function of time, blah, 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 with time. How would I find dz dx? Like, oh man, z is not a function of x. Z is a function of time. I know how to find dz dt, but it must be that t can be something with x. And so if you look at this, if I want to find the derivative of something with respect to x, I can take the derivative of it with respect to time and then multiply by dt dx, but really, I rearrange it just like I did here, that dz dx is really dz dt, meaning the time derivative of z, and then I'm going to divide by dx dt. Well, that's what this is. If you want to find the second derivative, you're trying to take the derivative of dy dx with respect to x again. That's what the second derivative is. The second derivative is the derivative with respect to x of the first derivative. Well, this z and this are the same thing, right? All I'm saying is, if you know how to take the derivative of z, what do? You take the time derivative of z and divide by another dx dt. Why do you do that? Well, it's really the chain rule. So how do you do it in this sense? Well, the formula I gave you in class is you take the time derivative of z, meaning the thing you want. Again, dx dt is not a function of x. Otherwise, we could just take the derivative. We have to take the derivative with respect to time, and then we have to multiply by dt dx, but that's the same thing as dividing by another dx dt, which we can find. Again, this is the formula I gave you in class. This is why it works. The second derivative of y with respect to x is really the time derivative of dx dt, of dx dy dx, divided by another dx dt. This is how you do it, and this is why it works. It's really the chain rule. If you just erase this and put a z, then we would do this. The time derivative of z divided by dx dt. dz dx. dz dt times dt dx, but this is the same thing as dividing by dx dt. This is a quantity we have because we were given either x and we can find dx dt, or we were just straight up given dx dt. Okay, hopefully that explains how to find this quantity, why it's the curvature, and the differences between dy dx, the second derivative of y with respect to x, because those things are not speed and they're not acceleration. That's all up here, okay? Speed and acceleration, those things are the things we love. This one is my least favorite concept. Dy dx is fine, right? It's really just a direction. It can also help us find the angle, right? The angle we're going is this angle right here. So if I ever ask you for the angle, that's just this guy, and we know how to find an angle, right? Tangent of theta would just be dy dt over dx dt, which is the same thing as just saying tangent of theta is just dy dx, which is saying that theta is just inverse tangent of that value. Okay, hopefully this helps explain that concept.